Okay, a very warm welcome in this section, and in this section we will be talking about decision tree, one of my favorite topic to talk on, as I will go in depth of decision tree to make you understand everything in decision tree with intuitive examples, with solved examples of decision tree. As I have seen on YouTube that they are some instructors are doing great job, but they are not doing depth into decision tree means for free. So I just want to make you familiar with decision tree, whoever is watching this tutorial, into depth, and I really hope that you will enjoy this section. But before that, what we are going to cover in this section are as follows. First, we will start with introduction to geometric intuition, basic intuition about decision tree, what the decision trees are. And then we will go further into how we will be building that decision tree. So for building, we will learn sub-concept, which is like entropy, information gain, Guinea impurity. Okay, then after that we will build our own decision trees, and then I will show you the implementation of decision tree. Okay, but before that, let's understand the basic intuition of decision tree, as there will be more topics which we will cover as I will discuss later on. Okay, so let's start. So first of all, what is decision tree? Decision tree is a supervised learning algorithm. Okay, so it is a supervised learning algorithm, and what do I mean by supervised learning is that we are having our x1 with our label y1 all the way down to the x2, then we have y2 all the way down to the xn, and we have yn. Okay, so we are having labels. So it is a supervised learning algorithm, and it is used for both, like support vector machine is used for both regression and classification. So it is used for both classification and regression. Okay, so you will see how we construct the decision tree like that. Okay, so let's start with the basic intuition of decision tree. So the definition of decision trees, that they are nested if and else statements. Okay, if you're a programmer, then you will be relating this concept, which is if and else, and the Python is a prerequisite, or any programming language is a prerequisite. So what is decision tree? It is just a nested if and else statement. So it is a nested if and else statement. So I don't know why it is so bold. So it is a nested if and else statement. So it just ask a question and it splits the data. Okay, so let me write the formal definition to make you more intuition behind. So they are nested if and else statements. Okay, so it's just ask questions, and splits the data. Okay, so it's just ask question and splits the data. So let me take one example of iris data set. Okay, so what we do in iris data set. So but let me make you familiar with what is this data set to make you more clear understanding of this topic. Okay, so iris data set is simply like this. You have a data set which has 4 features, like sepal length, sepal width, petal length, petal width. Okay, and you have the label, which is the species of that flower. Okay, so this is a task of flower species detection on the basis of 4 features. Okay, so this is a classification data set, binary classification data set. So you are having and like this. So let me change my color. I don't know why it is so bold. Okay, so you have like this. First you have sepal length, and then I hope that you understand what is sepal and what is petal. So sepal width, then you have petal length, and then you have a petal width. Okay, and then you have one more column, which is the label, which indicates what is species. So let's take an example: 2.2, 4.30, let's say 3.2, 4.6, and the label is setosa. Okay, so you have 3 classes in this data set as a label, which is setosa, which we label as 0, versicolor, which we label as 1, and virginica, which is labeled as 2. Okay, so the output will be either 0 means setosa, then either it will be 1 means versicolor, or virginica as in quote as 2. Okay, so that's the iris data set that I had just make you familiar with. Okay, so let's what we will do, we will not make use of any library, we will not make use of anything. We will simply what we will do, we will simply make a decision tree by yourself by making just if and else condition. Okay, so we'll make a simple classifier. Obviously it is not so formal, but we'll make a simple classifier that will simply classifies your flowers. Okay, so that's what we are going to do. So let me remove this, and I really hope that you understand what this data set is, and more if you want to more in detail about what the data set is, you can search online. This is a famous data set like iris data set, which is just for flower species detection system. Okay, so let's start. So first, here we have an variable x's. Here we have our x's, which is sepal length, sepal width, petal length, and petal width. Okay, so we are having these features, and we have a yi, which indicates either 1 or 2 or 2 or 0 or 2. Okay, so that's the basic intuition, means the data set part. We are given this data set. Now what we will do, we will make a classifier like this. First, if we write if, let me choose another pen. Okay, I hope that I should choose a better pen like this, blue. Okay, so if the petal length is smaller than some a, and a may be some number, let's say 2.3, a may be some number. If petal length is smaller than a, then consider y to be versicolor. Okay, so let's consider y to be 1. Okay, if not, if it is petal length is greater than a, then what to do? Oops, I hope that it is getting not clear. What happened? I have to buy my new computer. I don't know why it is so much lagging. Okay, so if it is smaller than a, the petal length, then consider your flower means a versicolor, and we have made one. And if it is petal length, if your petal length is greater than a, then what you will do, you will write else if sepal length, you take again one feature and says if it is smaller than b. If sepal length is smaller than b, then you consider your y to be virginica, means 2. Okay, if both condition fails, then say that your output is setosa. Okay, so here is our simple decision tree. We're using 2 features. We have made the decision trees using 2 features. So let me make it more intuitive. I hope so that you are able to understand. Okay, so that's why I'm speaking very slow. So here, let me tell you what if petal length, here we have taken 2 features, which is petal length and sepal length. Okay, we had not taken this 2 features. Okay, but you can make that. But this is not a formal decision tree. This is just for an example. This is obviously not correct. Okay, so you had to made one if condition, that if the petal length is smaller than some a, and a can be anything, 2.3, 4.3, that is usually I'm taking anything, but it is usually taken, which we'll see in one of our data set. We will see how it is chosen, and you will obviously see how it is selected. Okay, so if it is smaller than a petal length, then consider that y to be equals to 1. If it is not, let me check the recording is on. Yeah, okay, recording is on. Okay, so if the petal length smaller than a, then we consider our y to be this virginica. Okay, if the petal length is greater than a, or is this condition fails, it then goes to else condition, and in else condition this is again a nested if and is control flow. So check if your sepal length is smaller than b. If it is, then you say that y equals to virginica. okay? And otherwise, if this condition also fails, then it says else your y means y should be setosa, and you have this whole into this nested loop in this, and you have this whole classifier, and this is your whole classifier. So that this is the decision tree. Yeah, so let me make this diagrammatically in the terms of decision tree. So in terms of decision tree, we can write this if and else statement. First, we have our root node. First we make our root node like this. Let me make one root node. Here we have our root node with this condition: if a petal length is smaller than a, okay, then if it is yes, then you say your y to be 1, okay. If it is no, if your petal length is no, okay, you again make one more condition, which is sepal length is smaller than b. If it is yes, then you classify this y equals to 2. If it is not, then you take it as a 0, and your whole 3 variable target variables are covered. And this is the decision tree, and this is the decision tree I have made in yellow. This is the decision tree. Is just ask a question on the data set: if the petal length is smaller than a, if it is, then consider y equals to 1. If it is not, then again we have made another decision, and then we if it is yes or if it is no, like this. Okay, so this is the decision tree. It's damn easy like this. Okay, so here again I'm saying this is what you do. Just believe me. Yeah, this is the decision tree, and how it is constructed we will see. Okay, so we have made this if and else statement, nested if and else statement like this, and this is what the decision tree is. So here are certain terminology that we will have to see over here. So here are the details that we should know. Okay, so the first node, the head node, is known as a root node, or parent node. Okay, this is a root node. Obviously this is also a parent node, and these are the child node. Okay, child node, and this is the parents node, and this is also the parent node, and this is the terminal node. This is the terminal or leaf node, because you are not splitting this node into further nodes, so this is called the terminal. And this is also a terminal node. This is also a terminal node. Okay, this is also terminal or leaf node. This is sometimes called a leaf node when you are not splitting further. Okay, so this is a leaf node, or you consider it as a leaf node. This is the whole thing is called branch. This whole thing is called branch. This whole thing is called branch. Okay, and that's the basic terminology of this. Okay, and this is the splitting of your data. Okay, this is what you are doing, which is splitting. Okay, if you are removing some node, let's take an example this, then you are pruning it. Okay, then you are pruning this node, but we don't know, we don't want right now. Okay, so that's the decision tree, and I hope that you understood this example clearly, and I really hope that you will that you got a very good intuition of decision tree in much smaller span of time, in much easy way. Okay, so I hope that you remember this terminology. Either I will make you familiar with terminology by the time also, if it is not required for remembering all those things. Okay, but it's best to take a paper and a pen and write notes with me, whatever I'm writing. Okay, and just listen me carefully. After listening me, you can make notes. Okay, so now let's see what's the decision boundaries will look like. Okay, what's the decision boundaries will look like, or the hyperplanes will look like. But what do I mean with hyperplanes? I mean with hyperplane decision boundary is, let's take an example of linear regression. In linear regression, we are making a straight line. This is called the hypothesis, decision boundary. Then we have a hyperplane. This is called the hyperplane. In support vector machine, we are also making hyperplane. In logistic regression, we are also making hyperplane, means a decision boundary. So in the decision tree, we also have the decision boundaries, okay, or hyperplanes. So let's see how it is constructed. So I don't know I will be able to make that image or not, but I will fully try that. Okay, so here let me make one x and y plane, x and y. Oops, please anyone help me to make this. Okay, let me do that. Oops, I'm just freaking out. Let me do it again. Yeah, okay, great. So I have made one, and this is my x-axis. This is my x-axis, and this is my y-axis, and we have two features, which is sepal length and petal length. I think so, yeah. So we have petal length in the x-axis, and we have sepal length in the y-axis. Okay, so I have just made it. You can remove this y-axis. Maybe it will confuse you. In our x-axis we have petal length, and y-axis we have sepal length, because we have taken only two features in this example. We have not taken more features like petal width and sepal width. Okay, so what we consider, what we have done, we have considered this full reason. We have considered this full reason to be y equals to 1. Okay, this hyperplane, let's name it as a first hyperplane. So this full reason is our y equals to 1, means whatever data point will come is considered y equals to 1. And this is just the if statement that we have seen. If petal length is more than a, okay, then y equals to 1. So this is the full reason. Okay, means we have not further split, so it is just a full reason where y equals to 1 if that condition passes. Okay, then another hyperplane we can construct. Let me choose another pen. Another hyperplane we construct that this reason would consider y equals to 2. Okay, y equals to 2 if the sepal length is smaller than b. If the points come in this reason, then it will consider y equals to 2. Another we have hyperplane. Let me take another pen. Let me take another pen. Let's take an example of blue. Okay, another we can consider that as a y equals to 3. Okay, if that falls in this reason. So here we are constructing hyperplanes, and if something come here, then it's consider y equals to 1, it's y equals to 2, or y equals to 3 with these two features. Obviously it will be more dimensionally high when you plot the 4 features. Okay, so you can see that we have a hyperplanes where we are able to make predictions. Okay, and we have made a simple classifier. Okay, but something to note over here, that all your hyperplanes are axis parallel. Okay, are axis parallel, means this is parallel and this is parallel. So you can see over here that all the hyperplanes are axis parallel. Okay, so that's the I hope that you understood decision trees in depth, and this is the basic intuition that I want to give it to you in more sophisticated way, or not sophisticated, it's just a good way. Okay, so as I've tried it to keep it as simple as I can, and I kept it. Okay, so let's start building, or let's start with mathematical reason, that how we construct these kind of decision trees, how we construct. Okay, so but before that we have what we do, how we choose the variable, or how we choose the feature to be the root node or the branch, or this how we split. So we have an attribute selection measure, and if you select randomly, like I have chosen petal length, if you choose randomly, then you will be ended a very bad model. So we have different attribute selection measure, we like entropy, information gain, Guinea impurity, which we'll see in detail to understand how we select the attribute to be as a root node or like this. Okay, so let's take an example of this data set. If you want to split this data set, what feature you will use? What are you going to use? Outlook as your feature, root node, or temperature as a root node, or humidity as a root node, or wind as a root node. Okay, and play tennis is our label. So which you will use? If you choose randomly, maybe you will be ending up with a bad model. Okay, so you have to do that kind of thing. No, so we scientists or researchers have done a very great job. Even you all have to do all this kind of thing, research, and please keep contributing to the AI community. That maybe I'm also doing research in machine learning, and definitely will come up with something extra. Okay, so different measures are different attribute selection measure are entropy. We have entropy. Then we have the second number, we have information gain, which we usually write as IG. Then we have Guinea impurity, and simply IG. Okay, so we denote like this. Okay, so we will talk about all of these three, and I hope that you will understand each of them. Okay, so let's start with entropy. Okay, so entropy, let me write it more formally. Yeah. So first of all, what is entropy? Entropy is an attribute selection measure. It's the measure of randomness. Okay, how pure that attribute is to be used as sum nodes or a root node. Okay, so it's the measure of randomness. So let me write the definition, because definition is also important. And if you want this kind of all my notes, you can simply write with me along. Either you can comment or join the New Era community, Discord community, and ask me there. I will be able to give. Okay, so ask me there. I will be able to give all this entropy, etc. Is the measure of randomness. It's the measure of randomness. Okay, the higher the entropy is, the higher the entropy is, the harder to draw any information from them. Okay, so if the higher the entropy is, it's very hard to break your node, okay, or to choose the node. So our entropy should be low to be considered as a leaf node. But still, don't worry, I will dive into the cases to make you more understand what do I mean with these terms. Okay, but first of all, let's take I will show you one equation, and then I will show you how first of all one example, and then I will show you properties of entropy. Okay, so first of all, let's take an example where you are given, you have y to be maybe y1, y2, all the way down to the yk. And in this case, you are not, this is not examples, this is this is like maybe setosa, means what is the number of classes you have. Okay, so maybe you have binary classifier or you have a multi-class classifier. Okay, so what is the number of a classifier? So maybe you have in the iris setosa, we have here's setosa, Virginica, and versicolor. So here we have y equals to y1 to be setosa, then we have Virginica, then we have versicolor, means 3 y's. Okay, so that's what I mean with this. Okay, so let's first of all let me give you the equation. Okay, so the equation is defined as like this. H, we define our entropy by H equals to, let me choose white color because I like white much. Okay, minus this minus is very important, minus the summation I equals to 1 all the way down to the k, and k here is the number of your what is the number of a class. Okay, p of y, probability being y, log of base, and b is usually taken as 2 or e. Okay, to 2.713. Okay, so b is usually taken as 2 or 3, but we usually take b as a 2. So if you are taking b as a 2, then you can consider it as lg. If you're taking b as a e, then you take as l and natural logarithm, and you have a log 2 base, log 2 with the log with the base 2. Okay, this means lg. Okay, so you take log of p of yi. Okay, and that's the whole equation of your entropy, means it just measures the randomness. Okay, so let's take one example, because it is I know that is making no sense to you, and I know that is making no sense to you, but I will make sure that it will make sense. Okay, so first is we want to measure our randomness for playing golf. Okay, you want to measure your randomness for playing golf. Okay, so let me write play golf. Oops, let me write the data set first. What's the data set we'll be using? So we have this play golf data set, play golf data set, where if it is what is the number of yes, which is 9, and what is the number of no, which is 5. Okay, so this is our data set like this, and let me make this also. Okay, so this is a data set, and you want to take out the entropy of playing golf. Okay, playing golf. Okay, and here we want to take out entropy of being no, and being yes. Okay, so what you do first, you take out the entropy of 0.36 log to 0.36 minus, means this is your first yi, this is your first y, means yes, sorry, no, this is for no, and minus, let me make it up, okay, minus 0.64 log base to 0.64. okay, this is what we have, and the answer is 0.94. okay, so here what we are doing over here, that first we are writing this equation p of yi times the log of for no, and then we are writing for a yes. Okay, and there is subtracting, and we have entropy as 0.94, and it can be further split. Okay, so this was the basic calculation of entropy, but let's see some cases of entropy to make you more sense of this entropy attribute selection measure. Okay, so we will see some properties. So let's consider that we have y to be 2 class, means we have a binary classifier where we have 2 class, one is yes, and other one is no. Okay, any kind of yes or no, whether it is playing tennis or etc., it's yes or no. Okay, so let's take an example of let's take one scenario. Let's take one scenario number 1. Okay, so here is our scenario which tells, here is your data, and number of a yes is 99%. Number of a yes is 99% in your data, means these are your y labels. So we have 2 unique values in your y labels. So here you have yes and no. So in that case your yes is around 99%, and your no is about 1%. Okay, this is your case 1. So let's take out the entropy for this. H of y minus, you're taking minus 0.99, means 99 log, means LG, I'm writing log not 2, maybe I'm writing a log of 0.99 minus this is for my yes, means this is for my yes, because we have added a summation for each y variable. So we are doing for each y variable. Okay, minus 0.01, the log of 0.01, and your output is 0.0801. okay, so that's your entropy. Okay, so let's take one more scenario. Scenario number 2, and here let's take an example of your data having the yes to be around 50%, and your no is around 50%. Okay, so if you take out entropy of this, minus 0.5 log of 0.5 minus 0.5 log of 0.5, which is equals to 1. And the maximum entropy is 1, and it is very hard to split this. It's very hard. Okay, so its maximum entropy is 1. Let's take another scenario. and if you have a binary classifier, I'm taking an example, your maximum entropy is 1 if you have a binary classifier. If you have a multi-class, then the equation changes, okay, which you can see on the internet. But most of the cases, if you understand binary, you will be able to understand multi-class. Okay, let's take another scenario. Scenario number 3. Okay, scenario number 3 tells you that your D, which has yes to be around 0% and you have no to be around 100%. So your entropy over here would be 0. Okay, your entropy will be 0 and the minimum entropy is 0 over here. Okay, so you can see some cases that is, if you have ID3 follows, if you have some algorithm, means a decision tree follows that if you have entropy equals to 0, then you consider that as a leaf node. And what is leaf node? As your prediction. If your entropy is 0, then you consider that as a leaf node. If your entropy is 1, then it needs further splitting. Or if your entropy is big, means your entropy is, for binary is generally greater as like this. Your entropy is generally like this. Entropy is in between or equals to. Okay, so your entropy will be in this range. So some means algorithm follow ID3. There is one algorithm called ID3. It's a subset of decision tree algorithm. So ID3 follows if your entropy is 0, then you consider, or is small, then you consider as a leaf node. If it is 1 or large entropy, then it needs further splitting. Okay, so that's the entropy, and I really hope that you understood entropy in detail. So let me make you familiar with what we have seen so far. So we have talked about decision tree, which you can reverse back to see more, but I'm going to recapitulate the entropy. So what do I mean by entropy? Entropy is the measure of a randomness that measures if your attribute needs further splitting, or it considered as a root node, or it could consider as a leaf node, or like that. Okay, so we have taken one example of playing golf, and then we have taken some 3 scenario where we have seen that it is very hard to split. It is very hard to split if you have. It's very hard to get information if entropy is high, so it needs further splitting. Okay, so if you have yes to be 50%, no to be 50%, then entropy will be 1. If you have another scenario, then it will be like this. I just see the calculation. You can see the calculation if you want to understand it much better. Okay, so that's what this entropy is. But let's see the diagram of entropy visually. It's a bit interesting. Okay, it's a bit interesting. So let me draw one diagram of entropy. Okay, so here we have our, let me draw a good one. So here we have 0, here we have 1. Okay, so I hope so that I'm not able to draw it, but let me try at least. Okay, and the highest entropy is 1. The highest entropy is 1. Okay, is 1, and this is the diagram of entropy. This is the diagram of entropy. Okay, so the highest entropy can be 1 if you're taking with this equation. I have already showed you or proved you. So this is an example of entropy. Okay, great. So we have seen the entropy, which is the measure of randomness. So now let's talk about the another attribute selection measure, which is information gain. Okay, we'll talk about information gain. Let me write it down. Information gain, and I will take an example of, I will explain you information gain with the help of one data set, which is, I have already showed you. I thought I will give you a surprise with that, but I've already showed you. Let me show you again. So here we have that data set. Let me show you. Yeah, here is our data set. Okay, let me draw back like this. Okay, so here is our data set, which is play tennis. Okay, this is a play tennis data set, and what we will do, I will make you familiar. Just see this data set, look at this data set. I will be looking, I have already looked at. Okay, so here you have a play tennis as target variable, and you have these features. So we will see which feature to use or which feature to not. Okay, so here you can just see what you have around 1 2 3 4 5 as a no, and 1 2 3 4 5 6 7 8 9 as a yes. Okay, so we will you just see this, and now let's come back to information gain. To understand, first I will give you an overview of what information gain is, and then we will dive deep. Oops, where is my I don't know why my computer is lagging. Just give me a comment why it is very lagging. Okay, so here is my information gain. Okay, great. I hope that everyone is able to see. Yeah, okay, great. So let's consider you have the data set B. Okay, so you have the data set D like this. Let me consider this as a data set. Let me consider D. Oops, wow, we have a data set which is D, and what you do, you further divide this data set into your further data sets, further smaller subsets of this data set. And how we will divide this subset of this data set? It means that you divide this data set into versions. And what versions? Maybe let's take an example of iris data set. Okay, so what you do, you divide this setosa, versicolor, and virginica into 3 data set, which contains setosa, versicolor, and virginica. Okay, so whatever examples of setosa will go in this data set. Whatever examples of virginica will go in this data set. Whatever examples versicolor will go in this data set. So that's what you do. You divide your data basis on the number of labels, and I'm talking about binary classifier or classification task over here. Okay, so what you do, you divide your data set. First you divide for dv1, then you divide for dv2, then you divide it for dv3. Okay, dv3. Okay, and what you do, you take out the entropy, of this dv1, you take out the entropy of dv2, then you take out the entropy of dv3. Okay, and maybe there's this kind of setosa, versicolor, virginica. You take out the entropy, and then you take out the entropy of your whole data distribution. Okay, before splitting. So you take out the entropy before splitting, and then you take out the entropy after splitting. Okay, so you take out entropy before splitting like this. Okay, after that you minus it, you subtract your h of d. The function, the entropy means previous entropy, this entropy h of d, which is the entropy before splitting, minus, let me write it down, minus the weighted entropy, which is whatever the weighted entropy will come. So let's see how we, with the help of an example, what I'm talking about, how to calculate one example to make it more familiar. Weighted entropy, how do you take out the weighted entropy? So you just minus it with the weighted entropy. Okay, after splitting, entropy after splitting. So let's see how it is done in more detail. Okay, so I've just give you what the formula is. You just divide your data into subsets of your data, like divisions, and then you take out the entropy before the splitting, and then you take out the entropy after splitting. Okay, so let's see. So first let's take out the entropy of division number 1. Here I'm going to take out entropy of division number 1 with the help of that play tennis data set. Okay, so h of dv1, which is there we have 3 5, means first I'm writing for 3, means first I'm writing for yes. Okay, first I'm writing for yes, where we have our where we had divided our data set into a yes or no. So there we are having total of 5 examples, where 3 examples are yes and 2 examples are no in out of 5. Okay, then the entropy will be 0.64. okay, but you then again what you do, you take out entropy of your division number 2, it will be 0, and in the same way you take out the division number for division number 3, 0.97. okay, what you do, you take out the average entropy, and that's equals to 0.64. That's equals to 0.64, and the formula for calculating your weighted entropy is like this. Just wait for a few seconds. The formula for calculating your entropy, or weighted entropy, is like this. Let me write it down. First, what you do, you take out this. I think it's not 64. It's, yeah. So I will just multiply with the first division number 1. Here we at d1, the norm of d1 divided by d times the entropy of d1. Then what you do, you plus d2, the norm of d2, times entropy of d2 plus norm of d3, and this is the division number 3 data set divided by the norm of d. Okay, and this is your full data. This is d is the full data, so you take out the size of that full data. Okay, then you again d3y. okay, and then this is your weighted entropy that you get after all of this. After you've taken out the weighted entropy, then that will be equal to some number, and then what you do, you subtract your entropy, previous entropy, you subtract your entropy before the splitting, you subtract your entropy before the splitting minus you get after splitting. So let me write the formal equation for Ig, what you get. Okay, so Ig equals to y, and any var means variable. Maybe variable can be outlook, or temperature of that, from that, or windy, or humidity. Okay, so in that we will check if the higher the entropy, higher the information gain is, we can select that as a root node. Okay, so what you do, you just take the entropy of your data, full data, and then you means of your data, and then you minus it, minus I equals to 1 all the way down to the k. The norm of di means the division of your data, and this is simply the maybe setosa, or then versicolor, or yes or no, like that. So divided by the full d times the entropy of di. Okay, so this is your weighted entropy, this is your weighted entropy, and this is your entropy. Okay, before you're splitting, and then you will get the information gain for that variable. Okay, so we will see one more example later on when we will be building our own decision tree by ourselves mathematically. So again, let's recapitulate what we have seen so far. We have simply seen, so let's go back to that data set. So where is my data set? I don't know actually where. Yeah, here is my data set, and here what we do, we take this data set and we simply divide this data set into multiple divisions, into 2 divisions. Okay, so we divide this data set into yes and no. Okay, and whatever number of examples will come, we take out. Let's take an example. Here we have 9 over total number of data examples, and here we have a 5 over total number of examples. Okay, so what you do, you simply 9 by 14 log of 9 by 14 minus 5 by 14 log of 5 by 14. Okay, then you will get some entropy, which is your entropy of your data. Okay, entropy of your data before splitting. Okay, so that's what the entropy is, and I hope that you understood what I'm trying to say over here. and this is your for yes and this is your for no, because you have added a summation of your entropy like this, I equals to 1 all the way down to the k. Then you have a probability of yi minus the log of, means with base 2 probability of yi. Okay, so that's what we are doing. You are doing the same over here, but this time you have 2, so that's why you're doing 2, and this is only for binary. You can see equations for multi-class. Okay, so that's what the information gain is. And here what we do, we take out data and we divide our, first we take out the entropy of that data, and then we divide our data into multiple divisions. And here we have 3 categories, so we divide it into 3 categories. If you have 2 categories, you divide into 2 categories, and then take out entropy of that categories, and then you take out the weighted entropy. Okay, without rather taking out the average, you take out the weighted entropy of that after splitting these all. You take out the weighted entropy, then you subtract. And how you take out the weighted entropy, here is an equation. I'm going to give it to you. It's just I have already given, but more formally, this is the equation for weighted entropy. Okay, so what you do, you simply, it's the norm of d, means no, divided by what is the number of a full, means here we have number of a no, number of no divided by total number of examples times the entropy of that di. Okay, so that's how you take out the weighted entropy. So after taking out the weighted entropy, you subtract the previous entropy minus the weighted entropy. Okay, so that's what we are doing in information gain. I really hope that you understood information gain. Okay. Okay, so please see if on some blocks, if you want, either you can ask me in Discord server. I'll be very happy to help you in the new era. You can find the Discord server in any new era, new video on new era. You can find at it, and you can join, and there is a lot more that you can. And also, if you want to support, please kindly go to New Era YouTube channel, and please subscribe that YouTube channel. Okay, and if you can watch the whole tutorial on New Era. Okay, because you are going to get the whole ad free over there. Okay, so now we have seen entropy, then we have seen information gain. Now it's time for talking about Guinea impurity. Okay, so this is also the most famous, it's most similar and most famous that is used today, which is Guinea impurity. And it just equals to, it's very similar to entropy. It's a very similar to entropy. This is, I use things very similar sign. Okay, don't comment it like this. Just I have just said it like this. It's not I use thing. It's just it's very similar to entropy. So let me give you one equation. The equation for calculating the Guinea impurity. So I G, and it is not information gain. This is the sign for a Guinea impurity of y equals to the 1 minus I equals to 1 all the way around to the k, and again it is your y variable, not anything, it's the y variable. Again I have already seen y equals to yes or no, mean 2, or it also vertical, so unique values in your I times the probability of yi squared. Okay, so that's the thing. And again, it's if we take a same scenarios, how I'm saying it's if we take the same scenario as we have taken entropy, some scenarios. Let's take an example of scenario number 1, scenario number 2, scenario number 1, where your yes, we have, let's take you have y to be 2 class category, where you have unique value as a yes or no. Okay, so what is the probability, means what is the number of a yes is 0.5, and what is the number of a no is 50%. Okay, 0.5. Okay, so what will be the Guinea impurity? Guinea impurity will be 1 minus 0.25 is 0.25, because if you square this, because here we are squaring, so if you square this and again you subtract it, minus 0.25, then you are going to get a 0.5, and 0.5 is maximum in Guinea impurity. 0.5 is maximum. In entropy we have 1 as a maximum. If it is this 0.5, Guinea impurity is 0.5, then it needs further splitting. If it is 0, then it's not need, if we can consider that as a leaf node. Okay, so that's the scenario that we have already seen in, and if it is in the case of Guinea impurity, our Guinea impurity in this case where you have 50% yes, then that will be 1. So we have, but you may ask, here Ayush, what is the advantage of Guinea impurity rather than using the entropy? So it is an alternative to entropy, just to increase the just to make it fast. Because in Guinea impurity, if you have seen, we are just taking h of y equals to the minus the summation I equals to 1 all the way around to the k, p of yi minus the log of p of yi. So here you can see we are taking a log, and taking a log takes time. Okay, so as an alternative, researchers comes with a very easy and understandable way, 1 minus, and this can be derived. These are derived in information theory. Okay, but I'm not going to go in information theory, but you can see this is the for Guinea impurity, and this is most used as an alternative to Guinea impurity at entropy. Guinea impurity is most used as an alternative to entropy. Okay, so that's the thing, and I hope that you understood Guinea impurity also. So let me make you familiar with the diagram. So here is the diagram. Let me make first for entropy. First here is for entropy. So here we have 0, here we have 1. So here this is for entropy, where your maximum is 1, and this is for, obviously something will differ, so but the maximum is 0.5 in Guinea impurity. So yellow one is Guinea impurity and the white one is entropy. Okay, white one is entropy. So I hope that you understood the why I'm saying. But why we use Guinea impurity? Because it is more faster, because we are taking log and that takes time. So it's more faster than entropy. Okay, so that's the whole definition of whole decision tree, and I'm recording till 51 minutes, and I hope that you understood all of this. I hope that I've written a lot. Okay, so we have learned a lot, and I really hope that you understood also. Okay, so now we will make a decision tree classifier, and I will show you the decision tree numerically. Okay, how we do regression task and decision trees. Okay, so first let's do in a fast way. I do have not a lot of time over here, but I will show you this data set. So here is my data set which I'm going to use. Okay, so first of all, what we do, we take out the entropy. Okay, we take out the entropy of this whole data set. We take out the entropy of this data set, h of d. Oops, where is my pen? H of d, and simply what we are doing here, we have two y's. So here we are taking the entropy of our data distribution d. Okay, so that will simply equals to 0.94. As I've told that you have to take out entropy before splitting. Okay, for information gain. So we take out the entropy of this data set, as you have around 5 no and 9 yes. Okay, so in that way you can take it out. If I want to make, I can simply make like this: 5 by 14 log of 5 by 14 minus 9 by 14 log of 9 by 14. Okay, so after you calculate, you will get this. Okay, so but feel free to correct me if I do anything wrong in calculation. Okay, feel free to correct me in the comment box. Okay, in mathematics we do, I'm just doing it fast, just we have to remember the concepts. Okay, so after you calculate the h of entropy of your distribution, now what you do, you calculate the information gain. You calculate the information gain. You calculate the information gain. Okay, how? First you calculate the information gain for y with respect to outlook variable. Means you have to check how much information that outlook variable contains. Okay, so in outlook, here we have outlook variable. You can see over here that here we have outlook variable. So let me let me take out. So in outlook, if you see the y variable, we have in sunny we have 2 yes and 3 no's. We have 2 yes and 3 no's. Then we have in outcast we have 4 yes and 0 no's. Okay, then in rainy we have 2 yes and 3 no's. Okay, so this is your outlook variable, and here you have a 2 yes and 3 no's, 4 yes, 0 no's, 2 yes, 3 no's, and this is for sunny, this is for overcast, and this is for rainy, and you can see over here. Okay, sunny, overcast and rainy. Okay, so this you can see that if you take out the entropy of this h of d2 h of d2, then you will see that this is equals to 0, and you can take this as a leaf node, and it does not need further splitting. Okay, so you can take this as a leaf node, because this does not need further splitting. Okay, now what you do, you take out the entropy of this h of d1 of y. Okay, then you take out this h of d2 d3 y. Okay, so you have taken this data set, large data set. Okay, taken this data set and split. You've taken this feature and split it. Okay, so we have this before splitting, and then what you will do, you take out the weighted entropy, which is equals to 0.69. Okay, so what you would, for information gain, you simply subtract 0.94, means the previous entropy minus the weighted entropy is 0.69. Okay, and weighted entropy I have already shown you previously. Okay, and you do the same for temperature. Where in temperature you have y. In temperature, where you have around, you have 3 classes: high, mild. Let me see. High, mild, and hot. Hot, mild, and cold. Okay, so in hot we have 2 yes and 2 no's, and here we have in mild we have 4 yes and 2 no's, and then in cold we have 3 yes and 1 no's. Okay, then you take out like this, and then you do for humidity, then you do for humidity, and then you do for windy. Okay, then you do, and it's found that the information gain in outlook is very high. Okay, so what you do, you take that outlook as your root node, Okay, then you take that outlook as a root node, then you divide this. So here let me go to one of my favorite decision tree PDF, where I will just explain you what this is. Okay, so you take this outlook as a root node, then what you do, you divide this as we have divided into sunny, overcast, and rainy. Sunny, overcast, and rainy. And overcast, you can see that we have a entropy equals to 0, so it does not need further splitting, so we can consider that as a yes, means we have 4 yes, so we can consider that as a yes because it's very pure, and then it needs further splitting, and this also needs further splitting, and then at some point they also become pure, where the entropy equals to 0, so, or the Guinea impurity equals to 0, then you consider as a leaf node. Okay, so this is how we make the decision trees, and this is how we calculate the information gain. This is how we made our decision tree. Okay, great. Now I really hope that you understood decision tree, and now it's I also enjoy very much when I make these kind of tutorials, and because it's just amazing, just helping students to make this understandable things. Okay, great. Now as we have only talked about classification, so as regression is not too much hard also. So in regression, let me show you what we do in regression. So let me go to the scikit-learn decision tree scikit-learn. I hope that is stable. Yeah, here it is. So it explains very good. It explains in very good way. So let me make you what do I mean with this. So let me take an example of this, petal length and petal width. So in the same way, here what you do, your petal length is smaller than or equals to 2.45, then Guinea impurity is high, then you would split it. Okay, here the Guinea impurity equals to 0, then it does not need further splitting, but it needs further splitting, so it splits that. Okay, so here it seems to be overfitting, because if you leave the decision tree to ask as much question, then it will overfit. So what you do, you either stop at certain depth, you either stop your decision tree at a certain depth to make it more robust, or you prune your decision tree by removing some branches from here. Okay, and you can see the same way that we have seen that we have made this kind of decision boundary, hyperplanes. Okay, great. Let's see some more. Oops, I use Brave as my browser, but soon we'll try something. Please make sure that you can put your comment below if I can see. Okay, and regression, what decision tree we can apply in regression also. So you can see over here that here what we do, let me get back to some good pictures. Decision trees regression, but I will soon go to documentation to show you more sophisticated, in a good way. Okay, so here is my decision tree regression, and let's take an example of this. As you can see from this also, yeah, so here we have a good example. So here you have predictor and you have a target variable. Okay, so here what you have taken outlook, and then you divide into sunny, overcast and rainy, and sunny needs further splitting but overcast does not. Okay, so most of the time you average it, and then you take out 46.3. okay, and then you split it again. What you do is split it. If you take out the average, again I'm saying you take out the average. Okay, that's what you are doing. And again, if I go further into this, it is very well explained. You can go to this, it's very well explained. But yeah, it's only for regression, but it's so much of but what we do, we simply, again, the things are same. For attribute selection measure, you simply you can sunny, overcast and rainy. Overcast over here is we have 4. This is your leaf, this is so pure, so that's considered as a leaf. And then what you do, you take out the average like this, you take out the average, and then you take out the 39.8, 46.3 over here. After taking out average, then you split your sunny into false or true. Then if it is false, then your output will be 47.7, and if it is true, then it is 26.5. and the same way you do the regression. Okay, so I hope that you understood, and you can go again to understand it more detail. So what you do, you take out the hours played and hour average, standard deviation average and hours played, and then you count it, and then you simply do some calculation, and that's not too much hard. Okay, great. So we have seen so far about decision trees regression, and I really hope that you understood this also. Okay, so you can go to this node, this website, sadesad.com, decision tree reg. You will be able to understand it, but it's more important to understand attribute selection measure, because people usually confuse us at this, and we have taken lots of examples for this. Okay, great. So now what we will do, I will show you the documentation, the implementation for decision tree. I will show you the implementation of decision tree regressor and decision tree classifier. Okay, so that you can know, because it's very important to learn from implementation. Okay, so I will explain you in more intuitive way. So let me open my ink to go. I hope that I'm just using it. Let me see if this works for me or not. Okay, great. Let me choose this pen. Yeah, so here you can go to this website, thistable.com, and here you will be able to find more. You can go to scikit-learn.org and documentation of decision tree classifier. Okay, so here again is what is the criteria to choose the attribute. Here we have Guinea, and here we have Entropy. Okay, so Guinea is a default, you can choose Entropy also. Okay, the quality of a split, supported criteria is Guinea and the entropy is for the information gain. After splitter means, do you want to choose the best splitter or random splitter? Okay, best means it will choose the best, random means any randomly. Okay, max depth, this is very important hyperparameter which you can tune it using grid search CV, or a randomized search. Okay, you can tune it. Okay, so that's what you will do. And what you do, you just make your decision tree to, if you do not make, then it will overfed, or then your decision tree will overfed. Okay, so the maximum depth of the tree, okay, if it is default as none, okay, if you do, it will learn a lot, it will make a lot of decision bound, it will learn a lot until and unless its leaves are pure. Okay, so it will learn a lot, so that's why it will overfit. So this is a very important hyperparameter. Then again you have a minimum sample split, means here the default is 2. Again you have to tune it, the minimum number of samples required to split an internal node. Okay, an internal node is just that node, the minimum number of splits that require. Okay, this is 2, but you need to be very cautious into this. Okay, then we have minimum sample split, then we have minimum sample leaf, and then the minimum number of samples required to be at a leaf node. Okay, so what is the minimum number of samples required to be at leaf node? Again, it's 1, but you can also tune it, but it's not that, but it's very good to tune it using grid search CV. Then we have a minimum weight fraction leaf. Then we have what is the max features, means the number of features to consider when looking for the best split. If you have a larger number of features, then you can consider as an the default is none, but you can use this, but it also has some disadvantages. Okay, then we have a random state, control the randomness of your estimator. Again, it's you can read some more details on random state. Max leaf node, the grow of a tree in a best first fashion. It is a default none. It's just like a max leaf node, or the minimum impurity decrease. The node will be split if the split induces a decrease for the impurity greater than or equals to this value. But I've not used it if I say very much right. It's just a limitation that you can make to prevent overfitting. Okay, I think this is deprecated. Then you have a class weight. What is the default is none always. Then we have alpha non-negative value. So that's the basic intuition. Okay, so we had talked about this, and then you can see some examples, and then there is something called as let me show you. You can also use this as a understanding the decision tree structure. So I will just show you one example of this. Okay, so here you can use the graphist tool. To plot your decision tree like this. He has used tree.plot tree. It is plotting the tree like this. Okay, because decision tree has one more advantage. It is easy to interpret. Okay, so that's the basic intuition behind decision tree. Okay, so let's go to decision tree regression. Okay, so let me see where is regression. Okay, let me see one more. Great, where is decision tree regressor? Here it is. Okay, so in decision tree regressor, it can be used for for regression task also. So here you have to choose certain criteria. The function to measure, here we are not using any entropy, here we are using the quality of your split. You can use mean square error, means how much it differs. Okay, so mean square error or mean absolute error or Poisson. So you can see Friedman MSE, but most uses MSE or MAE or RMSE. Okay, a splitter, again it's best, again the same thing, max depth, obviously to control your depth to prevent overfitting. This is an important hyperparameter. Again, I'm saying this is very important. VVI, this is also a very important to tune. Okay, then you have minimum sample leaf, and then you have the same as we have discussed. Okay, and then you can see some examples of decision tree like this, how we make. And then there are certain methods like plot or etc. Then you have some examples which you can see from here. and this is usually you can use we will talk about ADA boost also later on. Okay, so you can see some visualization in this library, and decision tree is used to fit this curve with addition, noise, or observation, and it's just controlled by the depth of that by the max depth, and the blue line considers the 2 and the max depth to be 5. If you take that, it will perform very well on training set, but bad on testing set if you do not control your max depth. Okay, so we have talked a lot on decision trees, and I really hope that you understood decision tree in depth. Okay, so in the next section, the reason why I've taken this too long to make you understand decision tree, because it's very important concept to understand, and I think it's very important. Okay, so you can have a look if you want onto this notes. Okay, but you can ping me on Discord or LinkedIn. I will very happy to give you these notes if you're not able to write. Either I will recommend you to write these things. Okay, I will just you can ask me to make this all wrong. Okay, so that's it for this video, for this section. So sorry for this section, and my throat is also so much paining, but yeah, that's it for this section. And in the next section we will start with ensemble learning, and again then we will go to unsupervised learning, then we'll talk a little bit on neural networks, and then we will end up this course, and you will be having enough understanding of machine learning to get started making projects in machine learning and getting a job or internship, but you have to do a lot of practice. Okay, so you can do that. Okay, great. So thank you for seeing this section, and again, if you have any kind of question, you can ask me. To the new era, be sure to subscribe if you wanted to support this content. Okay, so let's meet at the next section. Till then, bye bye.